Hi there, Joshua here. Bob sold his Xbox for £200, which is £40 more than he paid for it. And I said to this kid, I said, what did he buy his Xbox for, I said. She said, to play Call of Duty. Or FIFA, she said. Let's get on with the lesson. Right, so welcome to this lesson on regular polygons. So what I'm going to do in this lesson, basically the goal is to sort of look at how regular polygons fit together, either with themselves or with each other. And to do that, to investigate that, we're going to talk about the angles inside regular polygons. I should probably first of all explain what a regular polygon is. So a polygon is just a 2D shape with straight sides. So it's got to be a closed shape, so it's a 2D shape with straight sides. And a regular polygon, regular just means all the sides are equal and all the angles are equal as well. So I've tried to draw sketches of some regular polygons, some classic ones. So you've got this one over here. This is a triangle, of course, but when all the angles and sides are the same, it's an equilateral triangle. Equilateral triangle. We've got a quadrilateral here, four-sided shape. Again, when all the sides and angles are the same, it's got a special name. It's called a square, as you all know. But when you get beyond four sides, regular shapes don't really have a special name. This is a pentagon, and if all the sides are the same and all the angles are the same, it's just called a regular pentagon. No special name there. A six-sided shape with all sides and angles the same. It's a regular hexagon. Regular hexagon. And 8 sides, regular octagon. Right, let's try and work out the angles inside these shapes, and then later on we can investigate how they fit together. So in an equilateral triangle, what are the angles? What are the size of these three angles? Well, you probably know that the sum of the angles in any triangle is one. It adds up to the sum is 180. The sum of the angles in a triangle is 180 degrees. Actually, I'll just write that a bit lower. So the sum is 180 degrees. And if all the angles are the same, that means they've all got to be 60 degrees. 180 divided by 3 is 60. So 60, 60, 60. In a square, you probably know all the angles are right angles, so they're all 90 degrees. So I'll just mark that in, 90, 90, 90. 90, 90, 90, 90. And if you add them up, you can actually see the sum of the angles is 360. The sum is 360 degrees. So you might be wondering, will the sum always be 360 in any quadrilateral? So if you draw a sort of like a random quadrilateral, something like that, is the sum of these four angles 360? Well, you can show it is quite easily just by splitting the quadrilateral into two triangles. So if I pick this corner and just draw a line across like that, you've got two triangles there. These three angles are 180, add up to 180, and these three angles are 180. So the total is 360. So in any quadrilateral, the sum of the angles is 360 because they can be split into two triangles. Right, now what about a regular pentagon? What's the size of each angle in a regular pentagon? Well, if we could work out the sum of all the angles, maybe by splitting into triangles just like we did with the quadrilateral, then we could just divide that answer by 5 to get what each angle is. So let's try and find the sum of all the angles in a pentagon. So if you just draw a random pentagon, how many triangles is that going to be split into? Let's just mark the angles, like so. So if you pick a corner and you split the shape into triangles by joining this corner to other corners, let's do it. So you can join to that corner, you can join to that corner. So that's 3 triangles. So these 3 bits of the angles add up to 180. These 3 bits add up to 180. And those 3 bits add up to 180 as well. So the sum of the angles is just 3 lots of 180, which is 540. So it's 3 lots of 180. This was 2 lots of 180. So it's 540 degrees, which means that the size of each angle, is, because it's regular, just means all the sides and angles are the same, the size of each angle is just 540 divided by 5, which is 108. So each angle is 108 degrees, 108, just draw them in, 108, 108, 108. Well, right, let's move on to a regular hexagon. So what's the sum going to be there? Well, it looks like the sum is just going up by 180 every time. Let's just check that. Let's draw just a sort of a random hexagon. Doesn't have to be regular. But just mark the 6 angles, like so. If I mark a point, let's split the shape into triangles. Now when you do this, it's important that the lines don't cross in the middle of the shape. So the easiest way to ensure that doesn't happen is just to go from one corner, from the same corner every time. So like that, and then like that, and then like that. And that way none of the lines will cross, and all the angles formed will be angles at the corners of the hexagon, which is what you want. So that's 4 triangles. So the sum of the angles is just 4 lots of 180. So 4 times 180 is 720 degrees. So to get the size of each angle in a regular hexagon, they're all going to be the same. So you just do 720 divided by 6, which is 120. So all the angles are 120 degrees. 120, 120, 120, like so. So let's do an octagon now. So I'll just rub these out. So let's find the sum of all the angles in an octagon. Now when you, so I'll just draw a sort of a random octagon. It doesn't have to be regular for this bit. Like that. So I'm going to split the shape into triangles. Now when you do that, you're joining one corner to all the other corners you can join it to. There are 3 corners you can't join that one to. You can't join it to itself, of course, and you can't join it to that side and that side because they're already attached. So you're not going to be able to join it. Sorry, you're not going to be able to join it to this corner or this corner. So when you're forming triangles, the number of triangles you can make is always the number of lines you can draw to form the triangles is always 3 fewer than the number of sides. So an octagon has 8 sides or 8 angles. So that means you're only going to be able to draw 5 lines because you can't draw lines to these 3 corners. So 1, 2, 3, 4, 5. So that's 5 lines. So an octagon has 8 corners. So that's 5 lines you can draw. So is that 5 triangles? 1, 2, 3. It's 6 triangles. Not 5, it's 6 because at the start you've just got one region, and then for every line you draw you're adding another region into the picture. So if it's 5 lines, it's going to be 6 triangles because you're starting with one region already. And then as you add a line, that's 2 regions, 3 regions, 4 regions, 5 regions, 6 regions. So it's going to be the sum is going to be 6 lots of 180. It's 6 triangles. So hopefully that wasn't too confusing, which is 1080, 1080. So each angle, to work it out, you just do 1080 divided by 8. If you do that on the calculator, you get 135. So 135 degrees.
135, 135, 135, 135.
135. So the number of lines you draw is always 3 less than the number of sides, but the number of triangles you get is 1 more than that, so it's only 2 less than the number of sides. So I mean, we could keep going. We could do a 10-sided shape is a nice one, like a decagon, a regular decagon. I don't know if I can draw that though. Oh dear, yeah, roughly. That's meant to be a regular decagon, 10 sides. So how many triangles could you split that into? Well, you could draw, it's got 10 sides or 10 corners, so you could draw 7 lines, whichever corner you went from, because there are 3 corners you can't join it to, itself and the 2 corners either side. So you could draw 7 lines, which means 8 triangles. So there'd be 8 triangles. You can see that like that. So there'd be 8 triangles. So the sum is 8 lots of 360. Sorry, 8 lots of 180. What am I talking about? 8 lots of 180, which is 1,440. Which means in a regular decagon, if I just rub this out, each angle is going to be that divided by 10. So it's going to be 144 is each angle. So I'll just draw it once. I won't write it 10 times. But each angle is going to be 144 degrees. What about a dodecagon? That's got 12 sides. Imagine a regular dodecagon. Shall I have a go at drawing that? We'll give it a go. No, something like that anyway. So 12 sides, just pretend I did that well. If it's regular, all the sides and the angles are the same. So how many triangles could that be split into? It's got 12 sides, or 12 corners. So you could draw 9 lines from one corner. 12 take away 3 is 9, which means 10 triangles. So the sum of all the angles in a decagon, the sum of all 12 angles, is 10 lots of 180. So you can only draw 9 lines, which is 10 regions, 10 triangles. So that's 1,800 degrees. And then if you divide that by 12 to find the size of each angle, because they're 12 equal angles, you get 150, I think. So the angles in a regular decagon are all 150 degrees. Right, so now we know about the angles inside some of the regular polygons. Let's talk about tessellations. So a tessellation is just a repeating pattern that can cover an area of any size, leaving no gaps. So in a tessellation there are no gaps, all the shapes fit together perfectly. And what I want to know is which of these regular polygons tessellate with themselves. And I claim that there are only 3 of them out of these 7 that tessellate with themselves. So can you work out which ones? Well, clearly squares are going to tessellate with themselves. So if you had a bunch of squares of the same size, you can fit them together, of course, and there'd be no gaps, and you could cover an area as big as you like. You can extend that in any direction. And the reason squares fit together is because around every point you can get 4 perfectly. Basically, the angles inside a square are 90 degrees, and 4 lots of 90 degrees make 360, make a full turn. So squares tessellate. What about equilateral triangles? Are they going to tessellate? Well, again, let's consider what happens around every point when you try and fit them together. So if I try to fit some around that point, that's 60 degrees, 60 degrees so far. So how many times does 60 go into 360? It goes 6 times. So I reckon you should be able to get 6 equilateral triangles around a point. 60, like so. And then of course you can continue that pattern on. You could just pick another point and do 6 around that point. Well, like that. Or pick another point and do 6 around that point. And so on. So equilateral triangles definitely tessellate because you can get 6 around a point. 60 goes into 360 6 times. What about regular pentagons? Do they tessellate? Well, let's have a go. So imagine you had some pentagons of the same size. I'm just going to put 2 next to each other. So let's consider what's happening around this point. So far, this angle's 108, this angle's 108. So far that's 216. I can definitely get another one in around that point. I like that. 108. That's 324 degrees so far, so I can't fit another pentagon in there. There's a 36-degree gap. 36-degree gap. So pentagons, regular pentagons, don't tessellate with themselves. And it's because 108 doesn't go into 360. It's not a factor. What about regular hexagons? Let's have a go at those. So just clear some space. So are they going to tessellate? Well, 120 does go into 360. It goes in 3 times, so that suggests you should be able to get 3 around every point. Let's see if that works. 120. 120. Again, just considering what's happening around this point. And yeah, that's 240. So if I add another 120, that'll be 360. So you can get 360. You can get 3 hexagons around every point, and then you could just continue that pattern on. So 3 around that point, or 3 around that point, 3 around this point, 3 around this point, and so on. So regular hexagons do tessellate. Regular octagons, if you try and do those, could have a go over here, like that. Just put 2 next to each other. 135 doesn't go into 360, it's not a factor, so I don't think you'll be able to get octagons around a point without a gap. Let's consider this point. That's 135, that's 135, so that's 270 so far. That's 90 away from 360, so there's a 90-degree gap here. 90-degree gap. Not big enough for another octagon. So regular octagons don't tessellate because 135 is not a factor of 360. 2 of them go into 360, but then there's a 90-degree gap. And I guess the same will be true for a regular decagon or regular dodecagon. You could get 2 next to each other, but the angles are too big to get 3 around a point. 3 lots of 144 or 3 lots of 150 is well above 360. So they don't tessellate. So the only ones that tessellated were the triangle, the square, and the regular hexagon, and that's because their angles are factors of 360. So they could perfectly fit around a point, or fit around every point. Now I said octagons, regular octagons, don't tessellate with themselves. You can see that here. But there is actually another regular shape you could get in that gap. You could get squares in the gap. So I'll just draw that. Just get rid of that writing. So you could get a square in this gap. It would fit perfectly. Because the sides of the angles in a square are all 90 degrees. And then you could continue that pattern on. So although octagons don't tessellate with themselves, it looks like they tessellate with squares. So around every point there are 2 octagons, 2 regular octagons, and a square. So 135 plus 135 plus 90 equals 360, and that gives you the 360 degrees you need. So around every point there are 2 octagons and a square, so octagons and squares tessellate together. I'll call this pattern 488 because around every point you've got a square and 2 octagons. So if you're looking for combinations of polygons that tessellate with each other, you've really got to find combinations of angles that add up to 360. So there are quite a few out there. There's a really nice one I know. I'll just draw it in a sec. I'll just wipe this off. A very nice one I know. I'll call it the 3, 4, 6, 6 pattern. Because around every point you have a hexagon, 2 squares, and an equilateral triangle around every point. So I'll just try and draw it. It's a really nice pattern. So hexagon, I'll consider this point 2 squares and an equilateral triangle. So the angle on the hexagon is 120. 2 squares angles and 90 of course. And this angle is 60 degrees. And if you add those up, you get 360. So those shapes fit perfectly together around a point. And you can repeat this pattern on to cover an area of any size. You just draw squares coming off the sides of the hexagon and just fill the gaps with equilateral triangles. And you could repeat that somewhere else. You could draw another hexagon over here, squares coming off the sides. Sorry, this is very messy. Hopefully you get the idea. And then equilateral triangles to fill in the gaps. Another hexagon over here, squares coming off the sides of the hexagon, and equilateral triangles to fill in the gaps. So you get these sort of ring structures. So that is another tessellation, 3, 4, 4, 6. You've got to be careful sometimes. Sometimes you might find combinations of angles that add up to 360, but it won't give you a tessellation. I'll give you an example of that just to finish off. I'll call the pattern 5, 5, 10 because it involves having a decagon and 2 pentagons around every point. So I'll just try and draw it. So I'm saying you can't make a tessellation out of this. 8, 9, 10, something like that. That's the decagon. I'm saying around every point you draw 2 regular pentagons. So like so. And the angle of the decagon is 144. The pentagons are both 108, 108. Now that actually adds up to 360, so that looks like it's going to be okay. And you can continue this pattern on by drawing a pentagon coming off each side of the decagon. And you get this sort of flower shape. So why did I say you can't make a tessellation out of this? Well, if we want a tessellation with around every point 2 pentagons and a decagon, there's going to be a problem when we try and extend the shape out. For example, if you pick this point over here, you've got 2 pentagons around it already, so we need a decagon, something like that. But you need to do the same with this point over here. It's got 2 pentagons around it already, so we need a decagon. And as you can see, there's a problem. The shapes start overlapping. You get this overlap here. So if you want 2 pentagons and a decagon around every point, things aren't going to fit together when you try and extend the pattern out. You're going to get these overlaps. So this doesn't actually work as a tessellation, although you can make sort of one flower out of it. But these work nicely as tessellations, and there are probably some others out there. So that's a bit of information about tessellations with regular polygons.